Hello, everyone. I'm Lori DeToro, Communications Manager for Turntide Technologies. Thank you for joining us today to learn more about the evolution of axial flux motor technology. We are thrilled to have Adam Nixon presenting for us this morning, live from our Gateshead manufacturing plant. Thanks so much for joining us today, Adam.
Thanks, Laurie. Nice to meet you all.
Before we get started, we have some housekeeping tips to share, and if you've attended one of our other webinars, you already know this, but for any newcomers, this presentation is being recorded and will be available on demand on the Current and Wave website. We will be taking questions at the end of the presentation, so please use the Q&A section anytime to ask questions, and we will answer as many as possible when we're finished with the formal presentation. We also have a link to our June webinar around the safety and reliability of lithium-ion batteries that's in the chat. So you can go ahead and register for that before you log out of this session. Remember, this is a live event and we are doing a tech tour of technology. So when we mess up, and we might, laugh along with us and remember that we're doing this live with you. I think that's it for housekeeping. We are ready to get started. Take it away.
Thanks, Laurie. So this webinar is titled The Evolution of Axial Flux Motor Technology. To start with, I thought I'd give a brief introduction to myself. So my name is Adam Nixon. I'm the Director of the Mechanical and Multiphysics Engineering Group within the Turntide Global Engineering Group. I've worked at Turntide for just over 7 years. I'm a mechanical engineer by education. And in my time at Turntide, I've worked in the development of several electrification solutions. So the axial flux motor technology that we're going to talk about today, radial motor solutions that we've developed for bespoke OEM applications, development of our e-pump portfolio at 24 and 48 volts that you can find on the website, as well as in the development of the lightweight e-fan range that again is available on the website. And over the last few years, I've been particularly involved in the development of our axial flux motor portfolio, both in the development of the platform offering, as well as involved in customer OEM projects. Next slide, please. So firstly, for those of you who aren't as aware of Turntide, I've got a couple of slides just giving a brief introduction to Turntide. So Turntide acquired 3 businesses in the northeast of England, centered close to Gateshead 4 years ago. So there was what was formerly Borg-Warner Gateshead, which previous to that was Sevcon. So they've got a rich history in the development of power electronics solutions. Avid Technology, who developed axial flux motors, e-pumps and e-fans, and Hyperdrive, who developed the battery solutions. So by acquiring these 3 businesses, alongside its existing portfolio, Turntide assembled a rich electrification portfolio able to deliver for a wide array of electrification challenges with our customers. Next slide. So again, covering the products that we have on offer, axial flux motors, low voltage and high voltage inverters, battery energy storage solutions, as well as e-pumps and e-fans. So focusing in on the axial flux motor technology, shown here is our existing portfolio of products that have been on the market for a number of years, and we already deliver to our existing customer base. So we have 3 main diameter classes of motor, 250 mil, 300 and 400 mil. And this technology that we offer is stackable. So you can see from the naming convention that a 125, 130 and 140 are a single stack, a one stack of those diameters. And then effectively the motors can then be stacked, and we offer that as a stacked solution. And then you can achieve, for example, there the 230 and the 240, which are a 2-stack 300 mil and a 2-stack 400. In terms of performance points, these different diameter classes and stacks allow us to meet the wide array of needs of different customer performance points. So on the higher speed side, our 125 goes up to a standard speed of 8,000 RPM with an overspeed up to 12,000 RPM. On the largest diameter, up to 5,000 RPM. And you can see the difference in continuous torque that can be delivered by those motors as well. So on the higher speed 125, 100 newton meters of nominal torque. And then on the larger diameters, up to 260 newton meters of continuous torque. So what this means is across this motor range, we can cater for a number of different applications that the axial flux motor technology is suited to, whether that's hybrid applications, whether that's ancillaries such as driving pumps or fans, straight in electric traction systems, as well as a wide array of other applications in aerospace and defense. Yep, next slide. So today we're here to talk to you about our new product offering that we're bringing to the market. So in the last few years, as we've been dealing with our customer base, taking in the voice of the customer and their requirements, while our Axial Flux motor technology does suit this wide array, we found a particular need for an even higher torque dense motor. So at the top, I've given a brief definition of these concepts. So torque density is the amount of torque that can be delivered divided by the weight. Power density is power delivered by the weight. And this is often used as a benchmark between different motor technologies. And what I wanted to speak to you today about is the benefits that Axial Flux technology gives over radial flux technology. So in the table on the left-hand side, I've detailed out an example turn-type motor against some equivalent radial machines. In radial motor 1, we're comparing to an equivalent machine with the same power level, so an equivalent 110 kilowatts, with a higher speed, which is typical of radial machines. In axial flux technology, the torque is proportional to the cube of the diameter, whereas in radial technology, it's equivalent to the square, or proportional to the square, should I say. So what this means is for an equivalent package and for an equivalent weight and power level, the axial flux technology can achieve higher torque. And the benefit of that can be seen in the right-hand side. So when we compare the axial flux motor against radial motor 1, which is the red line, for the same power level, effectively you have a higher speed and a lower torque point compared to the blue line, which is the axial flux motor technology. And when you have an application such as the orange point, which is the customers there with the diamond, effectively you can see that this is a lower speed, higher torque requirement. This is very typical of a lot of the customer applications we see, whether in traction, where typically the output wheel speed is less than 1,000 RPM. So with the differential, you're talking typically 3,000 to 4,000 RPM requirement. With ancillaries, whether that's heat pumps and fans, typically they have a speed range of about 3,000 to 4,000 RPM. So what this means is with the red radial motor 1 solution, to deliver the power as the customer requires it, this would require an additional system component. This would typically require a gearbox, which is an extra component with its own reliability, its own cost, and its own integration effort. The other option available to customers would be to go for an oversized radial motor, which I've shown here as radial motor 2. That's shown with the larger dash line in the yellow color. So what the customer would have to do here is they can achieve the low speed torque, as can be seen where the dash line sits above the diamond, but effectively they would have to oversize the product, picking a power level equivalent to 238 kilowatts. So this leads to higher cost on a unit basis, as well as additional active material that has to be used within the motor to be able to achieve the same requirement. And effectively, this example and case study that I've shown here is what's led us to develop a new product to our lineup. Next slide, please. So as part of the development, Turntide has used the best-in-class simulation and development tools. So we have access to the full ANSYS suite, which we use in our development program. So I've given a brief walkthrough here of the different steps involved as we went through the electromagnetic design for this new product. So we started with a review of the material manufacturing process and the available materials, undergoing a trade-off study to ensure that we're optimizing the grade of steel, the grade of magnets that are used in order to achieve the performance while minimizing cost and enabling manufacturing. We then reviewed slot pole combinations analysis. So the slots is the number of slots within the stator, the poles is the number of poles within the rotor. And what this allowed us to do is to be able to tune the performance of the motor against these two options to ensure performance. And as part of this, we used the ANSYS OptiSlang optimization tool, which allowed us to analyze thousands of different candidate designs and allow us to do the trade-off study, which is shown on the graph on the right-hand side. So this formed part of the design space exploration, where we looked at this large volume of prospective designs, and then we looked at the Pareto front, so the leading edge of those performance points, to identify the optimal candidate. Once we'd honed in on an area that we were interested in, we then went into detailed design, where we used 3D Maxwell to predict the performance and tune the geometry and parameters of the design. This also allowed us to ensure that this design could be manufactured at high volume. before the final activity to undergo detailed performance simulation. What this allows us to do is to understand the predicted performance, as well as key parameters that are to be used during the inverter pairing. So we can understand the performance, we can communicate that to customers at different performance points, so with different turns configurations at different voltages, as well as understand the matching with inverters that customers may be using, including our own range. Next slide, please. What that resulted in is the new product, which we've termed the AF430S. In this new naming configuration, we've switched around the structure of that. So the 430 is the nominal diameter, and the S at the end is for a single stack. So what we're introducing here is the single stack version, but the idea is that you also have the ability to stack this technology up to 4 stacks. So the naming configuration will be S, D, T, and Q. But today we're focusing on the S, and that's the product that we're having the upcoming release for. So on the left-hand side, we're showing the key performance specs. So this has a maximum continuous speed of 3,700 RPM, has an S2 continuous torque performance of 375 Newton meters, which equates to 120 kilowatts. For S2, which is the peak demand, we've characterized this on 20 seconds, and we expect a maximum peak torque of 875 Newton meters and 310 kilowatts, with a nominal maximum continuous current of 220 amps RMS. Of course, the caveat at the bottom, as with all motors, is that this is baselined on a standard set of operating conditions. So this is based on 55 degrees inlet coolant temperature. Of course, if the coolant temperature is lower, you can get more performance. If it's higher, the performance will be reduced. And on the right-hand side, we can see the performance map, which is fairly typical for a machine where you see reducing torque as you go up in speed, up to the base speed. As a point of note, the solid line that sits in the middle of the contour plot is the continuous line, and the dashed line, the black line at the top, is the peak. And the contours there show the different efficiency bands. So you can see there you've got a peak efficiency across the whole map of up to 97%. Next slide, please. So this is how this sits within the product lineup that I just went through a few minutes ago. So what this means is that the nominal diameter of this motor is slightly larger than our existing portfolio. So the previous largest motor was 400 mil nominal and the 140. This is slightly bigger at 430. It is slightly lower speed, with the maximum continuous speed coming down from 5,000 to 3,700. But the continuous torque is much higher than the other single stack options available. As with the other technology, this will be stackable. It benefits from the compact axial length, and on the right-hand side, the image there shows the 430, which we also have here on the camera, and it's also water ethylene glycol cooled. Next slide, please. So in terms of envelope, this is a representation of the GA, just showing some of the critical dimensions. So you have a PCD for the mounting at nominally 411 mil. You have a number of dowel holes, which I'll talk about as we go through the product walkthrough. The top box has a width of 160 mil, and you've got a center to top box height of 286, whereas a center to bottom height of 240. And the shaft to shaft length of 125. The weight of this, when dries, 42.6 kilos, not including the coolant, of course. Next slide, please. So I just want to talk about some of the features before we go into the product walkthrough. So as mentioned just before, we see a peak efficiency of 97% across the whole peak performance map. But within the continuous region, we see a peak continuous value of 96%. This is equivalent and achieves the highest efficiency class of IE4, which means it's suited to all applications, including industrial applications, which now are pushing for this higher IE class. Similar to our existing Axial Flux motor range, it utilizes indirect liquid cooling, which typically we recommend is water and ethylene glycol, and that's how the performance has been rated with. This motor in particular, which I'll go through in the walkthrough, utilizes a through shaft female spline. So what this means is that you have a shaft input or output on both sides of the motor, so that this motor can directly be used in series hybrid applications. And we've also utilized a female spline within this, which on our standard product is based on ISO 4156. We're designed for operation up to 850 volts VDC, which meets the higher voltage classes that we see in modern electrification systems, and peak over voltage support up to 1 kilovolt. Due to the inherent benefits of the Axial Flux technology, we see relatively low cogging torque and torque ripple. This obviously results in smoother system operation and low NVH characteristics. As mentioned, it's a stackable motor design platform. So if you were to stack this product, you would be able to effectively double the torque. Product configuration. So as part of the release, we will have elements of this that can be configured. Some of this I'll talk through as we go through the product walkthrough. But additional element is that within our offering, we will have different stator turn configurations. So for those of you familiar with stators and electromagnetic design, effectively we'll be able to change the number of turns, the amount of times that the strands you have in hand unwinding go around the stator teeth. This will lead to changes in the optimization for different voltage systems within the vehicle. So you'll be able to increase the turns as you go to higher voltage classes, which will reduce the phase current requirements. Similarly, if it's a lower voltage system, you'll be able to reduce the turns to be able to achieve the full performance map. And we will be offering two options with the top box, one for high voltage glands and one for the Amphenol power lock range, depending on system conditions. It's a durable construction. So as you'll see during the walk around, this is going to be an aluminium die cast housings and top box. And we're undergoing a validation plan according to ISO 16750. In terms of ingress protection, we'll also be rating it to IP67 and IP6K9K. Next slide, please. So for the product walk around. Okay. So to start with, I wanted to show some of the features on this front face. So we have two main options for concentricity alignment with the product. So we firstly have dowel holes within the motor, which can be used to maintain concentricity, as well as a spigot feature, which we've newly introduced in this product. So this diameter that sits within these raised castellated regions can be used for a mating spigot feature, which is a very common feature on existing technologies such as gearbox and flywheel housings. This is shown here with a dummy shaft for marketing purposes, so it doesn't show the female spline, but effectively within this circular feature here is where the female spline would be sitting. We have a fully bolted and sealed coolant system, which is accessed via the hose tails, which I'll show in a second. And the features here would be used within the stacking if we were to deliver a stack technology. So multiple of these motors can be bolted together by turn-tied as part of our build configuration and provided as a package solution. So if you come around to this side here, you can see up close the top box. So this is shown with the gland configuration using standard glands. We're also going to have the option for the Amphenol power lock, which will be available at certain turn and voltage classes. There's a fully sealed top box, which as a customer you won't need to access. So when we're providing this with the glands, we'll be providing cable as well, specified to the customer requirement. Down here, we can see a threaded mounting point, which can be used during assembly for lifting. So I've just shown some examples of some lifting eyes here. So they can be bolted in on either side. And then when in application, this can also be used for grounding. So we have this marked as a grounding point as per CE requirements. If we come around the back, you can see that it effectively looks nearly symmetrical. So again, that means that it can be used in a through shaft application. So you can access the spline from both sides. So you can have a shaft coming into this side as well as the other side. If you want to deliver power from both sides, or if you use in the series hybrid application. What this also enables is when you look kind of bigger picture here, and you have the coolant ports on one side and this gland configuration on the outside, if you just zoom out just a slight touch, that effectively, as part of our build configuration, we also offer the option to be able to configure this in both directions. So if as a customer you want to have the coolant ports and the high voltage connections on the opposite side like this, we can offer that. If also you want these to be aligned, we can do that as part of the build configuration. And then if we come around to the final view, You can see the identical mounting and ground point on this far side, which again can be used for ease of integration using the lift and eyes, and then also for earthing in the vehicle. And for demonstration here, I've fitted just some fairly standard stainless steel hose tails. As standard, we ship this without any fittings. So it's a BSP thread. So that gives versatility and flexibility for the OEM integration. At the top here, we can see the TE low voltage connector, which is used for providing the signals from the PT100s that are embedded within the windings for monitoring temperature, as well as for the resolver signals. We also have the option for a bearing temperature sensor, which can be fitted as an optional part. Generally, you can see as well that all of the components, the major components, so the two main housings, the seal plates, the top box and the lid, all cast aluminium. So what this ensures is a rugged construction, and that by itself, this motor is durable. It doesn't require any major adaptation or additional framework by the customer to be able to integrate this and ensure a robust product. And also that effectively the customer can mount from both sides with bell housings or otherwise. So this can form part of a continuous structure. Okay, that's it for the walkthrough. Okay, next slide. Okay, and now that we've went through the product walkthrough and some of the key features, I wanted to just give an example of an application case study. As part of the formation of the voice of customer and looking at the requirements that drive the development of this product, as well as some of the feedback we've had just over the last couple of years as we've been talking to some target customers, we've seen a real growing demand and trend for diesel hybrid systems. So that's one of the key applications that I wanted to talk to you about here. It's not the only application, but we feel that it's one that this motor is very well suited to. So as an example, a hybrid internal combustion engine powertrain with a requirement for electric motor, direct drive with no space for a gearbox. Again, this isn't the only configuration that this can be paired with a diesel engine, but it's one that I thought I would talk to you about. So the challenges that you would have in integrating a traditional radial flux motor option is, as to my previous point, you would potentially have to oversize the motor, which could lead to packaging challenges in itself. But even without that, a radial solution is typically longer in length compared to the very short axial flux motor technology. What that means is you're adding length and you've got more of a packaging challenge to be able to fit that in line with the motor and the prop if you're using it in a marine application or within the drive line in an automotive application. You would have a weight penalty in using a radial solution alone with the motor, but also potentially with the requirements to have a gearbox as well, which is the last point is in having that gearbox, you would obviously have a penalty cost, added system complexity, potentially packaging challenges of itself. So our solution is this 430S product. So short axial length, enabling the transmission layout, high torque density. And on the bottom left, I've shown an example of a diesel engine performance map with an image on the right. So what you can see from that is that you've got maximum torque at somewhere close to 2,600 RPM, with a requirement just above that up to 3,000 RPM. So if you think back to the performance envelope for this motor, which has a maximum speed of 3,700 RPM and typically a base speed somewhere around 3,000 RPM, effectively you're utilizing all of the power of that machine at the same speeds as the diesel engine. So you don't have to oversize your machine. You can have highest efficiency close to the operating point for the engine, so you're not operating it in a low efficiency region. And it enables a multitude of different performance modes when coupled with a motor, whether you're using it for generation, whether you're using it for low speed acceleration or a torque boost. It really does enable a multitude of different options. One of the final points is that because the form factor and the way that we've designed the spigot feature, and also because the diameter, what it allows is really easy integration with the flywheel housings that you'll typically see on the diesel engine system. Next slide, please. So now we're going to the Q&A.
Thank you so much for that great presentation. Loved the tech walk around. As we begin taking questions, please continue to ask more if you have them. We'll get to as many as we can, and if we don't get to all of them, we will post a Q&A blog with the answers on the website. We do have several questions already in. So Adam, I'll ask you the first one. Is it
Yep.
possible to apply the winding made with the hairpin technology to the axial flux motor?
Sorry, can you repeat that?
Is it possible to apply the winding made with the hairpin technology to the axial flux motor? I think a hairpin winding.
Yes. Yes, it is technically possible. Uh, hairpin has been explored and developed for radio solutions. It does offer some benefits, but it also does have some drawbacks and increased manufacturing complexity to be able to achieve the connections between the hairpins. Um, we don't see that as a needed requirement for our technology um, because of the geometry of the stator slots and the way that we can insert the coils. So we don't see the need for the added complexity to be able to integrate that. And we can achieve a very good fill factor as well.
Okay. The next question we have is, does the sealing, the IP67 and IP6K, 9K, require any additional protection in the shaft area?
So the shafts have, this design has integrated shaft seals. So buried within and underneath this cover plate, we have integrated shaft seals that sit in front of the bearings to protect the bearings. So the bearings are sealed in themselves, but as an additional layer of protection, we've integrated shaft seals on both sides. And actually, one of the points that I didn't mention during the product walk around is that we also have an integrated through shaft resolver, which is also buried within this package. So it's quite hard to believe, but again, within this really short space form, we have obviously the rotor bearings on both sides, shaft seals, as well as the resolver.
So the next question, and I'm probably going to say this word incorrectly, so I'm going to spell it for you. Is this Halbach, Halbach array configuration?
No, it's not. So compared to other axial flux motor technology, which uses a whole back array, we just have a more simple arrangement of magnets using a consequent north-south pole arrangement, which simplifies our rotor manufacturing technology.
Okay, yeah, lots of questions coming in, Adam, so be prepared to stay there for just a minute. This motor is liquid cooled. Just want to know if the coolant flows through the stator coil.
Yeah, good question. So unfortunately, I haven't got the product open to show you here, so I'll have to describe it as best as possible. Um, but effectively, there's coolant cooling both stators, but it's indirect. So again, underneath this plate, there's effectively a cooling jacket that encompasses this whole surface here. That sits within an aluminium enclosure, and the stator sits on the back face of the far side. So you have aluminium, your liquid coolant, aluminium, and then your stator to extract the heat via conduction. So it's not direct cooling, which again we see on some of the other solutions where they require direct oil cooling, which involves product risk, but also complexity. So this is indirect liquid cooling using water ethylene glycol, which is typical for a lot of existing combustion engine systems. And effectively, the coolant is split equally between both sides of the motor. So when it comes in here into these two ports, one being the inlet and one being the outlet, there's effectively a coolant rail, and then the coolant goes around and cools indirectly both stators before returning to the common outlet and combining together.
Excellent. Does axial flux motor technology have an effect on the bearing discharge problem for the shaft bearing?
Yeah, interesting. I mean, bearing discharge, you could do a multi-hour lecture just on that topic alone. From the research we've done, from the testing we've done, and from the engagement with the industry experts, we actually see very low risk. I mean, you can never say zero because it requires years and years of testing, but a very low risk. Um, we actually have also integrated a Aegis ring effectively within this design to allow the pass through and reduce the buildup of voltage on the rotating assembly. But from the research and development that we've done, we see very low risk within this topology.
Excellent. I'm going to ask this next one, but if I get anything wrong, the person who asked the question can respond. So it says the 20 kilowatt range for any AF motor, is it available or not? And is it more compact?
Sorry, can you repeat that?
Sure. It's kind of a broken question. 20 kilowatt range, any axial flux motor, is that range available or not? And is it more compact?
I'm not quite sure what that question refers to with the 20 kilowatts, unfortunately.
Okay. If you ask this question, could you give us a little more info in a new question? That would be helpful. So how much cooling is required, and can you talk about that a little bit more?
Sure. So I think the nominal value off the top of my head is 8 liters a minute, which is the nominal point that we suggest. Any lower than this flow rate, and you will see obviously an increase in temperature for the amount of coolant that you've got, as well as potential thermal effect, which may reduce the performance rating. If you go higher than that 8 liters a minute, we don't really see much of a benefit in terms of the performance. You effectively have a 1 over x curve where you have diminishing returns with higher flow rate. And we feel that the 8 liters a minute that we rate these to is a reasonably standard number compared to looking at other electrification components. So when you look at inverters and batteries, that's a fairly standard flow rate. And when you see the pressure drop for this, which unfortunately I don't have to hand, it's a reasonably low pressure drop for the amount of flow that you require. So it means that you don't need to have a much larger pump to be able to deliver the cooling requirements to cool this.
Great. Do you have any applications in BEVs, battery electric vehicles? How can we replace traditional radial flux motors with this axial flux motor in a battery electric vehicle?
Absolutely. And we have customers today who are developing battery electric systems, full electric systems, and they're using them as part of the traction system. And so these customers in particular are using them as the only traction motor solution within the vehicle. Of course, it's all dependent on the transmission layout, what you're doing in terms of, are you doing all four-wheel drive? Are you doing two-wheel drive? How are you setting up your differential, etc. But yeah, we already have existing customers who are looking to integrate this, and we expect that to grow even further with this expanded offering that we're now producing.
Great. I knew the answer to that was yes. What type of maintenance has to be done with these axial flux motors, and how often?
These are actually designed as being maintenance free. So the typical maintenance points might be the bearings, but the bearings we've selected and integrated within this are sealed for life. There effectively are no other maintenance points. Again, the shaft seals, the windings, any other degradable component has been designed as such to have safety factor to be operational and no degradation in performance over its intended life.
Excellent. So the next question is, what is the breakaway point in the ratio of diameter to length where axial flux motors are a better choice instead of radial flux? For example, what is the minimum diameter that can be achieved that provides higher torque with respect to a radial flux?
Good question. So from the analysis that we've done, and this is continually evolving as our tool chain is developing and as we're able to push more out of the axial flux motor technology. But as of today, we see the 125, so the 250 millimeter diameter, is still providing benefits over its radial flux counterparts. We see that below that diameter, there is a larger risk or more of a challenge to be able to achieve a benefit. And that's, I guess, unexpected because, again, the benefits of axial flux technology is in utilizing the diameter and that diameter cube relationship. So if you go to a really small diameter, and you do see some applications that have very small axial flux, it's not typically because you're trying to achieve more power. It could be some specific characteristic of the performance curve that a customer wants. But in terms of our
Right.
product portfolio, we see that the 250 mil today as being the smallest that we're offering.
Okay. Excuse me. The next question is, are your designs rare earth material free? How much would this impact the performance?
Our range today utilizes rare earth magnets, and we obviously appreciate that that's very much a hot topic. But what we see from the market and the technology today is to be able to achieve the high performance requirements that our customers demand across all applications. That's only achievable with rare earth magnets. What we've tried to focus on, especially in the development of this, but across all our motors, is being able to maximize the performance for the given amount of rare earth material. So that's a characteristic that we baked into our development process, is looking at the newton meters and kilowatts that we can achieve per kilogram of active material with a heavy focus on the rare earth magnets. And we certainly can achieve higher number of newton meters per given kilogram of rare earth magnets.
So related to that, someone also asked, are we considering a rare earth free machine at some point in the future? I know we're
Well, from an
always
engineering,
looking at different things.
so from an engineering perspective, we have quite a healthy pipeline of different developments that we're currently exploring. Of course, unfortunately, we can't discuss that, but
Right.
we have a number of different topologies that we're currently exploring. Obviously, R&D and development is always focused on goals, and that's certainly something that we are exploring.
So I'm going to go back to the 20 kilowatt question. They were asking for a maximum, let me go back and look, maximum power of 20 kilowatts. And the rest of that question, there are so many. Let me find it. Um, for a maximum power, is there a maximum power of 20 kilowatts in any axial flux motor that you know of?
Okay, so from our product portfolio, all of the different diameter classes, so the 125, 130, 140, and now the 430S, deliver above 20 kilowatts. But we do see a number of customers, especially again with the lower speed requirements, who will still utilize our technology, even though they're not utilizing the full datasheet performance point. That can be for a number of reasons. It can be because they're using it at lower speed, so all motors will be oversized. But at least with the axial flux, given the lower speed, higher torque skew, you're utilizing at least a higher percentage of the power. It can also be because some customers are running the coolant at higher than the 55 degrees nominal rating. So if you're running at higher than 55 degrees nominal rating, you reduce the amount of power that you can deliver. So in actual fact, where you see customers that are running closer to 85, 90 degrees of coolant, they're effectively reducing the rated power of the machine. So in answer, all of our motors can deliver 20 kilowatts. It comes down to the torque speed profile requirement as to whether these motors are the correct fit. But I would say compared to any other motors on the market, you certainly will be able to use more of the power of the motor.
Okay, with this axial flux motor used in parallel hybrid Class 7 heavy duty trucks, what would be the benefits in fuel consumption? This is very specific. What would be the benefits in fuel consumption when driven on freeways constantly for 500 to 600 kms?
Okay. I think this sounds like one of our potential customers has a really interesting application that I'm sure we'd love to hear about. Unfortunately, I don't have any numbers off the top of my head, but what I would implore you to do is to be able to contact the sales team, which there's a link at the end of the presentation. And I'm sure our application team would love to be able to answer that question for you.
We'll definitely get someone in touch with you. Um, let's see. What is the operational life?
Yeah, this is always an interesting question. So as most people will be aware, the lifetime of a motor in particular is dependent on the duty cycle, so the torque speed profile, the coolant temperature that the motor sees, the temperature that the windings are going to see as a result of those two factors, the environmental conditions, so shock and vibration loading, as well as loads that you see on the bearing. So if in the way that this has been integrated into the system, you see higher axial or radial loads. So what we've done is we've taken an average representative duty cycle and then representative cooling conditions, and we've been able to achieve 20,000 hours with this product from our prediction. But of course, it is heavily dependent on the application. Any of these factors could change effectively the degradation of the bearing, which we see is the most likely failure point at the end of life. So normally what we would do is, as part of early engagement between the customer and the applications team, we would really delve into the specific application, different operational modes, expected use cases, and we could take the detailed information from that better understanding of the application to be able to predict the lifetime of the product. And we like to do that with the customer. You see a lot of competitors who do just give kind of boilerplate answers, but that can be misrepresentative. So we like to really get into the detail with our customers to really understand the performance of the machine in their application.
Excellent. The next question is, do you have applications for aircraft propulsion, eVTOLs, and a path to certification by aviation authorities? Another interesting application
Yeah.
question.
Yeah, certainly another interesting application. So yeah, we've been engaged with a number of different customers over the last few years for those types of application. As the current puts out there, there's certainly a certification challenge that we see across the industry, and it's certainly a developing situation. So it's something that we're currently exploring. I wouldn't say that that's one of our key current markets and applications, but it's not because we're not interested in it. It's just a very early market with a lot of uncertainty in terms of the path to certification. So it's something that we'd certainly be keen to discuss with potential customers. As we see from the technology, again, with the lower speed, higher torque density, that's perfectly suited to turbo machinery. So I mentioned before pumps and fans, but also for blades as well, for takeoff in drones or eVTOL.
The next question is, are the stated performance parameters achievable also if it is used as a generator?
Yes, that's correct. Yes. So when you look at the motor and generation points, they're effectively nearly identical or symmetrical as you go from the kind of first quadrant to the fourth quadrant. But again, if you contact the applications team, we can provide the detailed performance maps, but it's virtually identical between the two.
So we have another cooling question. Can the cooling be made using lubricating fluid from the application where the motor is used, so there will not be an external source of flow for cooling the electric motor?
So I think this question might mean regarding alternative fluids for cooling. Again, please correct me if I'm wrong in the comments, but we see a number of customers who are currently engaging with who are using alternative liquids. So that might be oil or dielectric fluid. Similar to my other answer, it all comes down to the specific detail, but generally we have seen other customers who have used other fluids to indirectly cool the product. Typically with these different fluids, you may have a difference in specific heat capacity and density, which can affect the cooling behavior. So you may see a drop in performance for using those fluids. But of course, if you haven't got water ethylene glycol on these systems, it can be worth taking that very slight reduction in performance for not having to integrate another system. So yes, we can accommodate different fluids, and again, we'd be keen to work through that and understand what our machine can deliver in those systems.
Excellent. I don't know if we can answer this live, but we may be able to answer it in an email later regarding the slide with the comparison of turn-tide versus radial 1 versus radial 2. Is there a cost comparison available?
Can you say that again? Sorry, what was the end part of that?
Is there a cost comparison available for the axial flux motor versus a radial flux motors?
Yes, I think if you engage with the sales team and the applications team, they'll be able to talk you through the performance benefits relative to cost that you can achieve.
Excellent. Okay. Hang on. What levels of shock and vibration have been used during the design process? And I know we do testing. And has this been proven with testing?
Yes. I'm trying to rack my brain from memory. We actually ended up, for the development of this, of developing our own profile, vibration profile. What we found is when we reviewed the 16750 standard and looked at the vibration profiles on offer, there are a number of different ones available for commercial vehicles, for passenger cars, directly engine mounted, for electric motor type applications. But we saw that when we looked at those different profiles, um, we had this problem that some of the profiles had a lot of high decibels at higher frequencies, and some had a lot of high decibels at lower frequencies. Some had the sine wave on top, so sine on random, and differences in shock loading. And that led to us a difficult position where we didn't want to just test to one of those standards and have, because of the wide array of different applications that we have, always kind of be on the back foot and have this kind of challenge where we didn't suit that specific application. So we actually developed our own vibration profile for the validation of this that attempts to cover a number of those different applications to give our customers peace of mind. Um, we've already done testing on the development samples for this motor solution, as well as on key sub-prototypes for the motor to address items in the DFMEA that we encountered as part of the development program. And we're currently due to soon start the final validation program, where we'll be repeating some of that testing. Hopefully that answers the question. But
I think
again,
it does.
if you engage with the applications team, we can talk about specifics of vibration profiles and shock loading.
So I'm going to ask this. I think the answer to the question is probably yes. But if the cooling fluid has contamination, such as metal particulates, would that affect the lifespan or performance of the motor?
I guess potentially. So in the design for this, what we've attempted to do is to try and maximize the minimum aperture within the cooling profile. So we actually have picked a slightly larger um, threaded hole for the inlet and the outlet. And as you look through the coolant rail and the channel that passes in directly around the surface of the stator, we've actually tried to maximize that aperture size to ensure that there's no small bottlenecks that could be filled with debris. Of course, from a system perspective, we always recommend that there's a filtering system to generally protect the cooling system, not just the motor, but things like the inverters, which tend to be more sensitive. But within our design, we have tried to make it as robust and rugged as possible because we know that not all systems are perfect and that inevitably you will have debris within the system.
So I answered this privately, but someone asked if we have a presence in India to support, to provide support and to provide the axial flux motor.
Yeah, I mean, absolutely. We have Tintat has an entity within India, and we have an operational center there, including sales, engineering, applications. And we're currently working and developing a number of different customers and applications. So we're seeing a lot of growth over the last couple of years, and in particular over the last 9 months in Tintat India.
Excellent. I privately messaged this person as well that we might can get in touch with some of the specifics they're asking for because they're asking for brands and models. But I'll ask the general question to you. Can you give us an example about passenger or commercial vehicle applications in battery electric that are using axial flux motor only, an axial flux motor only?
Yeah, I mean, obviously this is a challenging question for me to answer because of commercial sensitivities. But we have a number of different platforms that are currently developing or using the axial flux motor technology, ranging from, let's call them off-road type vehicles, some of the more performance type vehicles, as well as through to some of the larger kind of truck bus platforms that we're currently developing. Of course, there are a lot of challenges with some of the larger class vehicles on a system level to be able to achieve the battery capacity that's needed. So historically, a lot of the development has been regarding hybrid systems, but we are seeing that slow shift as technology improves towards more fully electric platforms. But again, if there's any particular interest there, and if a customer wants to understand what benefits the axial flux motor technology could offer, then I would obviously implore you to engage with the sales and applications team, who can go through your specific application, and we can highlight and demonstrate what our technology can offer compared to other solutions.
Excellent. I probably have time for a couple more questions. The next one is, what is the maximum operational internal temperature of the motor? Where is the internal temperature sensor located? And what factors did you consider when deciding its location? That's a lot.
That's a great question for somebody who knows motors. So we've integrated the PT100 temperature sensors within the windings of the stators. So they're directly embedded within the end windings. So the end windings are the copper windings that protrude from the stator core. And the reason that we've selected that location is due to testing that we did. So we did testing with samples where we ran them at different duty points with different cooling temperatures. And in that test, we had a test sample with a number of different PT100s embedded at different locations. So we had them located at different points around the circumference of the windings, so at different kind of clock positions relative to the top box, as well as at different radial positions. So the inner windings, the outer windings, and then through different points in the slot. And then from the heat map that effectively was generated from that, we then looked firstly at our correlation to our thermal models, because we're always keen to develop them further. But what we found is we found that the highest temperature point was in the end windings at the outer, close to the phase cable exits, which is the location that we put those into. And that's controlled during the winding process and the drawing to ensure that the temperature sensor is embedded in the same location or within tolerance every time. And you effectively have two within a single stack. So because we use two stators and a twin stator configuration within our technology, you have a PT100 within each stator. And that means that you can monitor and measure both points.
Excellent. And can you share any of the off-highway applications where axial flux motors are being, just in general terms, that axial flux motors are being used, since you mentioned off-highway?
Oh, yes, of course. Yeah, so we see some quite interesting different applications. So we see, of course, some traction types where we see hybrid applications and the motor being used as a generator or in a boost. So that could be series hybrid or an off engine where it's purely being used as a generator. We also see in some of the off-highway applications, because of the much larger sizes and the requirements for what's the term for it? For the tools, for the implements. That's the word. So we see that actually the motors are being used to actually drive directly some of the implements to drive the hydraulic pumps. Again, to enable fuel savings instead of coupling off the diesel engine, as well as in some of the other components. So in some of the new applications, there can be quite large cooling requirements, which can lead to some quite large fans, 60 to 100 kilowatts. And again, the axial flux technology is very well suited to fans because of the lower speed, higher torque profile. So it's quite a wide array. And even on the traction side, this could be a more traditional setup where you have one larger motor going to a gearbox or direct drive. And we see some other applications where effectively they're using multiple motors, so up to 4 motors, one per wheel, enabling torque vectoring and all-wheel drive operational modes.
Excellent. Well, that is all we have time for today. We appreciate the numerous questions we got. Adam, thank you again for this very informative presentation. We appreciate you taking the time.
No problem. Thank you, Laurie, and thank you all for joining.
Yes, attendees, thank you for joining us. The webinar will be available on demand in about 48 hours, and we hope you'll join us for the next webinar. The link to that, again, is in the chat, and we hope you have a great week, and thanks again, everybody.
Thanks.